When you look up at night, the sky feels calm. Stars appear to drift without order, like glowing dust scattered on a sheet of velvet. But what seems random is anything but. Every point of light above us moves with purpose. Every orbit, every swirl of gas, follows a hidden rhythm that began billions of years ago. Our galaxy, the Milky Way, is not a still picture. It is alive, turning slowly in the darkness. More than 400 billion stars trace their paths around a single invisible center. Planets, dust, and clouds of gas follow the same curve. Even our own solar system is caught in that motion, circling the heart of the galaxy at over 500,000 miles an hour. One complete journey takes 240 million years. The last time Earth was in this exact place, dinosaurs walked across its continents. Civilizations rise and vanish while we make a single lap. Yet through all that time, something immense holds everything together. At first, astronomers thought the combined pull of the stars was enough to bind the spiral arms. But their calculations did not fit the facts. The stars on the outer edge moved too fast. According to the math, they should have flown away into deep space. Still they stayed. Something powerful, something unseen, was keeping them in place. Imagine a city at night. From a hilltop, you see ribbons of light moving through the streets. You can follow their paths, yet the traffic control room that guides them remains hidden from sight. You know it exists only because of the order it creates. The Milky Way works the same way. At its center lies a source of gravity strong enough to shape the galaxy itself. It has no visible glow. It sends out no light that our eyes can see. But its presence is written in every orbit, in every motion of every star. Dust clouds block our direct view toward that core, hiding it behind a curtain of shadow. Still, the pattern it creates can be traced, like footprints in sand that lead to a place we cannot yet reach. Somewhere beyond that dark barrier sits the anchor of our galaxy, the silent force that keeps everything from drifting apart. And this is where our story begins. For centuries, people believed the structure of the Milky Way was simple, a spiral of stars held together by the shared gravity of its own mass. Every star pulled on its neighbors, forming a grand, balanced system. It sounded elegant, and for a time, it seemed to explain everything. But when astronomers began to measure the speed of stars across different regions of the galaxy, they saw something that made no sense. The stars far from the center, where gravity should have been weaker, were moving far too fast. They were racing through space as if bound to something enormous, something much heavier than all the visible stars combined. It was as if an invisible hand was tightening its grip around the galaxy. The equations worked only if an unseen mass, millions of times heavier than the Sun, sat at the center. Yet, when telescopes searched that region, they found nothing. No bright cluster of stars, no glowing nebula, only darkness. To imagine it, think of holding a powerful magnet beneath a table covered with iron filings. The filings arrange themselves into curved lines, revealing the presence of the hidden force beneath the surface. You cannot see the magnet, but its effect is undeniable. Our galaxy behaves the same way. Its shape, its motion, even its very stability, point toward a force that cannot be seen directly. A presence buried in the direction of the constellation Sagittarius, far beyond the reach of visible light. Through most of the 20th century, this region remained a mystery. Ordinary telescopes were blind to it, blocked by clouds of cosmic dust that swallowed every ray of visible light. Astronomers could only guess what lay beyond. Then came a new way of seeing. Radio waves, longer and stronger than visible light, could pass through the dust. They became our eyes in the dark. In the early 1970s, two astronomers, Bruce Ballack and Robert Brown, turned their radio instruments toward the galactic center. What they found was astonishing. A compact, brilliant source of radio energy, brighter than anything else in the Milky Way. It was not a star, not a cluster, but a single point smaller than our solar system, radiating with enormous power. They named it Sagittarius, a star. The asterisk was not decoration. It was a mark of caution. This was something special, something that did not fit any known category of celestial object. Yet the mystery deepened. When astronomers looked for the same object with optical telescopes, it vanished. No light, no color, no glow. It was as if the most powerful source of energy in our galaxy had made itself invisible. Imagine hearing a person shout from a dark room. You know exactly where the voice comes from, but when you look, no one is there. That is what Sagittarius A star was to astronomers, a cosmic voice without a visible body. Radio studies continued. The emissions revealed magnetic fields so intense they could twist the paths of charged particles into knots. The energy output from this invisible region was staggering, far beyond anything a star could produce. If this power came from a single object, it had to be compact, dense, and unimaginably massive. The numbers pointed toward one extraordinary possibility: a black hole. But proving it would require watching how gravity itself bent the motion of nearby stars. It would mean tracking the orbits of stars that danced in darkness, racing around something no telescope could see. And that search was about to begin. For most of history, stars were symbols of permanence. They marked seasons, guided sailors, and outlasted civilizations. They seemed fixed, eternal, unchanging. But near the center of our galaxy, that illusion falls apart. In the 1990s, two teams of astronomers began an extraordinary project. Using the most advanced infrared telescopes on Earth, they turned their gaze toward the core of the Milky Way. Infrared light could pierce through the thick dust that had hidden the region for centuries. For the first time, humanity could see what was happening in that dark heart. What they found defied every expectation. They discovered a cluster of young, brilliant stars orbiting around an apparently empty point in space. These were not gentle orbits like those in our solar system. The stars were moving at extreme speeds, whipping through space in narrow, elongated paths. One of them, named S2, became the key to the mystery. It was a hot blue giant, bright and massive, completing a full orbit every 16 years. During its closest approach, it reached speeds of more than 17 million miles an hour, fast enough to circle the Earth 7 times in a single second. At its nearest point, S2 came within only about 11 billion miles of the invisible center. That might sound far, but in cosmic terms, it is incredibly close, less than the width of our solar system. Imagine a star the size of the Sun racing that near to something no telescope could see. If it were orbiting anything less massive, the speed would rip it free into deep space. But instead it curved back, perfectly on track, as if caught by an invisible hand of gravity. The numbers told a simple, inescapable truth. Whatever sat at that point had to weigh more than 4 million times the mass of our Sun, yet occupy a space no larger than the orbit of Mercury. No cluster of stars could fit those conditions. No gas cloud could stay stable under such pressure. There was only one known object in the universe capable of holding that much mass in so little space: a supermassive black hole. As more stars were tracked, the evidence grew stronger. Each one moved as if pulled by the same dark anchor. Their orbits were precise, predictable, and centered on the same invisible point. Gravity was writing the story, and it was a story only one conclusion could tell. The Milky Way was being held together by a monster, a black hole at its center. Astronomers now had their proof, but the challenge had only begun. They could measure its gravity. They could map its influence, but they still could not see it. To truly understand the heart of our galaxy, they would need to find a way to capture the unseeable, to take a picture of darkness itself. How do you measure something that cannot be seen? How do you weigh a presence that hides behind dust, absorbs light, and bends space itself? For astronomers, this became one of the greatest challenges in modern science. The answer would come not from what they could see, but from what they could measure through motion, time, and mathematics. Every star near the galactic center became a messenger. Its path, its speed, and its shape carried silent information about the invisible object controlling it. And in that information lay the truth. The key star, S2, was watched obsessively for more than 2 decades. Its complete 16-year orbit around the unseen center provided the most precise test of gravity ever attempted beyond our solar system. Astronomers tracked every subtle curve, every small shift in brightness, every change in its position. When they plotted S2's orbit, the path was not perfectly circular. It was an elongated ellipse that passed astonishingly close to the galactic core before sweeping far out again. The closer it came, the faster it moved, obeying the same laws Isaac Newton had described centuries ago. Laws refined by Albert Einstein to include the effects of relativity. By combining these laws, astronomers could perform a cosmic scale measurement. The result was precise and staggering. The invisible mass at the Milky Way's center was about 4 million times the weight of the Sun. The uncertainty was less than 1 part in 1,000. In human terms, it was as if someone had weighed a mountain from thousands of miles away and gotten it right within a handful of grains of sand. But mass alone was not enough. To confirm what it truly was, scientists had to define how large this hidden object could be. If it had a solid surface, S2 would have crashed into it during one of its close passes. Yet the star always survived, skimming the edge of something that never revealed itself. That meant the central object was smaller than the distance of S2's closest approach, less than 11 billion miles across. To hold 4 million solar masses in that confined space, its density would have to be beyond comprehension. Even if it were made of neutron star matter, the densest known material in the universe, it would still collapse under its own gravity. No force could resist that much weight. No structure could stay intact. There was only one conclusion left. This was not a cluster of stars. It was not a ball of exotic gas or a swarm of dark objects. It was a single point of unimaginable gravity. A supermassive black hole. Astronomers gave it a name worthy of its place in the heavens: Sagittarius, a star. It marked not only a discovery, but a turning point in our understanding of reality itself. Yet proving its existence scientifically was not enough for the human mind. Numbers and graphs could convince physicists, but they could not satisfy the deep human urge to see, to visualize, to witness. For centuries, humanity had looked into the skies and asked questions that began with, "What does it look like?" We had painted galaxies, mapped nebulae, and photographed stars. But how do you photograph something that swallows light? That question would lead to one of the boldest experiments in the history of science. In the early 2000s, a new idea began to form. If one telescope could not see the black hole, perhaps many working together could. By linking radio observatories around the world, scientists hoped to create a virtual telescope the size of Earth itself. The larger the telescope, the sharper its vision. This global collaboration would come to be known as the Event Horizon Telescope. Its mission was simple to describe and nearly impossible to achieve: to capture the shadow of the invisible. They were not chasing light, but its absence. The goal was to image the glowing ring of gas and dust surrounding the black hole. Matter heated to billions of degrees as it spiraled toward the point of no return. This fiery halo would outline a perfect circle of darkness, the event horizon. To achieve that, telescopes from Chile, Spain, Mexico, Hawaii, Arizona, and even the South Pole had to work in perfect synchronization. Each recorded data onto massive hard drives, collecting radio waves that had traveled 26,000 light-years to reach Earth. The synchronization was so precise that even the Earth's rotation and atmospheric distortion had to be corrected to a fraction of a microsecond. For years, the data sat locked in laboratories, awaiting processing powerful enough to make sense of it. It took supercomputers, complex algorithms, and human patience to combine petabytes of raw information into a single image. Then, in 2022, the wait ended. For the first time in history, humanity saw the shadow of its own galactic heart, a faint, glowing ring surrounding a perfect circle of black. It was small, faint, and blurry, but it was real. The image confirmed the calculations, the decades of work, and the theories of Einstein written more than a century earlier. The bright ring showed matter glowing at temperatures of billions of degrees as it fell inward, twisting around the black hole at nearly the speed of light. The dark center was the event horizon, the line where time and space themselves fall inward and cannot return. This was more than a picture. It was a moment of contact between mathematics and reality. The invisible had been seen. Astronomers looked at that ring and saw not just light, but history. The story of a galaxy, of stars born and lost, of space itself folding in on its own weight. The faint orange glow came from material that had been drifting through the galaxy for eons, only to meet its end at the very heart of creation's shadow. In that image, the universe looked back at us. The invisible had become visible. The theory had become truth. But this was not the end. The image raised deeper questions about time, gravity, and the limits of what we can know. The closer we look at Sagittarius, a star, the more reality itself seems to twist into something unfamiliar. For at the edge of this dark circle, even time begins to change. Time is something we take for granted. It flows quietly in one direction, second by second, heartbeat by heartbeat. We measure it with clocks, but we feel it with memories, with aging, with change. We think of it as constant, but near a black hole, even that certainty breaks. Around Sagittarius, a star, time does not behave like it does on Earth. The deeper you move into its gravitational field, the slower time passes, not in theory but in measurable reality. This strange effect, predicted by Einstein more than a century ago, is called gravitational time dilation. And near the heart of our galaxy, it can be seen in action. When astronomers observed the star S2 during its closest approach to Sagittarius A star in 2018, they saw something remarkable. Its light shifted toward the red end of the spectrum, stretching into longer wavelengths as if pulled by invisible hands. This was not a trick of motion. It was time itself stretching under the weight of gravity. Einstein's equations had said it would happen. The data confirmed it. At the peak of its orbit, S2 was moving at nearly 3% of the speed of light. From our vantage point on Earth, its light weakened and reddened, just as predicted. What those measurements meant was astonishing. Time near Sagittarius, a star was running more slowly than time here. If you could somehow stand on a planet orbiting close to that black hole, your seconds would not match hours. You would live slower without even realizing it. 1 hour near the event horizon could pass as many years for the rest of the galaxy. It is not science fiction. It is nature itself, reshaping reality. Imagine being there, close enough to see the stars above you appear to shift, bending around an invisible sphere. Space would not look flat or calm. It would seem to ripple, as if the universe itself were liquid. You would look up and see the past and future reflected together, light curving around you in ways the mind can barely imagine. The airless silence would not echo, but your instruments would scream with distortion. Radiation would pulse like waves of color beyond human sight. Time on your clock would tick faithfully, yet an observer far away would see it slow, like a movie stuck in endless slow motion. This is not just the bending of light, it is the bending of time. The closer you get to the event horizon, the more dramatic it becomes. At that boundary, the point where escape becomes impossible, time, from our perspective, almost stops. If you watched an object fall toward the event horizon, you would never see it cross. It would appear to slow down, frozen in place, fading from sight as its light stretched redder and redder until it vanished completely. From your viewpoint, it would hang there forever. But for the object itself, the story would be very different. From its own perspective, it would cross the boundary in moments. It would feel no wall, no flash, no resistance, only the smooth, unstoppable pull toward the center. Both experiences would be true, and that is what makes black holes so strange. They do not just bend space, they change the meaning of reality itself. At the event horizon, the laws of physics that we know begin to falter. Gravity becomes so strong that even light, the fastest thing in existence, cannot climb out. Beyond that line, space and time trade places. Moving forward in time means moving inward, toward the singularity. No engine, no technology, no force of will could resist it. The path forward is written by gravity itself. Yet this slowing of time is not a curse. It is a gift to science. It allows astronomers to test the very limits of general relativity. The way light bends, the way time dilates, and the way stars move, all of it matches Einstein's predictions with perfect precision. It means our understanding of gravity, even under the most extreme conditions in the universe, still holds true. But there is something haunting in that perfection. Because if time can slow, if it can stretch almost to a stop, what happens to the future beyond that edge? For all our equations and experiments, there is one place we cannot follow: inside. Beyond the event horizon, our instruments, our math, our light, our signals all fail. Time becomes tangled, space collapses, and causality, the idea that every effect follows a cause, loses meaning. The universe outside continues, unaware. Stars are born, worlds spin, life evolves. But within that horizon, reality folds in on itself, silent and unknowable. And yet, this darkness shapes everything we see. The orbit of S2, the spiral of the Milky Way, the balance of gravity that keeps us alive. At the heart of all creation lies this paradox, a place where time stops, yet existence continues. It is a reminder that the universe is not made to be simple. It is not here to comfort us. It is here to astonish us. And so scientists began to look deeper, past the event horizon, into the motions and mysteries that unfold where light itself begins to lose the fight, because to understand what happens there is to understand the final shape of reality itself. There are moments in science when imagination becomes reality, when the boundaries of theory dissolve and something once thought impossible takes form before human eyes. The first image of a black hole was one of those moments. For decades, scientists dreamed of seeing what could not be seen. Black holes, by definition, swallow all light. They have no surface, no glow, no reflection. Photographing one seemed as absurd as trying to take a picture of the wind. Yet the universe always leaves traces of its secrets. Matter that falls toward a black hole does not disappear quietly. It screams its final light into the void. Gas and dust swirling toward the event horizon become superheated, reaching billions of degrees. Before vanishing forever, they shine brighter than entire stars. That glow, bending around the black hole's gravity, creates a halo, a ring of fire circling darkness itself. It is not the black hole we see, but its shadow outlined by the last light of dying matter. This idea inspired a bold vision: to capture that shadow, to turn the most mysterious object in the cosmos into something visible, measurable, and real. It began with a network of radio telescopes scattered across the planet, from the icy plateau of Antarctica to the volcanic peaks of Hawaii, from the deserts of Chile to the mountains of Spain. Separated by thousands of miles, these observatories would not work alone but together, synchronized by atomic clocks ticking with precision beyond imagination. Linked by a method called very long baseline interferometry, they would combine their signals into one colossal instrument, the Event Horizon Telescope, an Earth-sized eye, capable of resolving the tiny region of space where Sagittarius A star hides 26,000 light-years away. The challenge was staggering. The target was so small on the sky that it appeared the size of an orange resting on the surface of the moon. The signals from the telescopes had to be aligned to within trillionths of a second. Even the rotation of Earth and the faint distortions of water vapor in the atmosphere could ruin the view. But humanity persisted. In April of 2017, every telescope in the network turned its gaze toward the heart of our galaxy. For several nights, they recorded faint whispers of radio waves emitted by the gas spiraling around the black hole. No single observatory could see the whole picture. Each captured fragments of a cosmic puzzle, thousands of terabytes of data. These fragments were then shipped on hard drives to supercomputers, because even the speed of the internet was too slow for the task, and then began the hardest part: the waiting. Years of work went into decoding, calibrating, and aligning the signals. Teams of scientists across continents compared results, removed distortions, and refined their algorithms. It took patience that could only come from curiosity stronger than doubt. In 2022, after 5 years of analysis, the data finally came together. What appeared on the screen was not an artist's impression, not a simulation, but reality itself. A glowing ring of light surrounding a perfectly circular shadow. There it was, the center of the Milky Way, Sagittarius, a star, a ring of fire, 12 million miles across, glowing in shades of gold and orange, marking the boundary between existence and oblivion. Every feature of the image matched Einstein's predictions. The light closest to us appeared brighter, amplified by motion toward Earth. The far side appeared dimmer, as light struggled to escape against the pull of gravity. The dark circle in the middle was the event horizon's shadow, the last silhouette of light before it fell forever. That image was more than science. It was a window into time and truth. It proved that the strange mathematics of relativity, written more than a century earlier with pencil and paper, could describe a place where even light loses the race. For astronomers, it was like hearing the universe whisper, "You were right." The photograph also gave us a new sense of scale. The black hole's shadow was vast, its diameter about 12 million miles. Yet, seen from Earth, it appeared impossibly small. To resolve such an image required a telescope the size of the world itself. And so, in the collaboration of hundreds of scientists and dozens of nations, humanity built that eye across continents. It was a symbol of what curiosity can achieve when united by a single purpose: to see what was once invisible. But the image was not still. Beneath that calm ring, matter was moving. Swirls of plasma raced around the black hole at nearly the speed of light. Their brightness changed from moment to moment, flickering as magnetic fields twisted and reformed. The structure was alive, dynamic, forever changing. It was not just a photograph of the present, but a snapshot of movement, light captured on the edge of eternity. For every person who saw it, the meaning was different. For scientists, it was proof of physics. For poets, it was the shape of mystery itself. For humanity, it was the first glimpse of the heart that has always guided our galaxy. And yet, as breathtaking as it was, it showed only the surface of a deeper truth. Because behind that glowing ring lies a world where the laws of time and space no longer hold. What lies beyond that darkness cannot be seen, but its effects ripple outward across the stars, across the spiral arms, across the thin line of light we call the Milky Way. The image was an ending and a beginning. It confirmed what we had always suspected, and it dared us to ask new questions. What happens to matter once it crosses that line? Where does time go when it stops? And what does it mean that the center of our galaxy, the anchor of everything we know, is a hole in the fabric of space itself? As scientists studied the image, they saw more than confirmation. They saw motion. They saw patterns. And in those patterns, they realized something else. Sagittarius, a star, is not silent. It stirs. It breathes. And sometimes it awakens. For years, Sagittarius, a star, appeared calm. Too calm. If this truly was a supermassive black hole, why was it so quiet? Why didn't it behave like the violent quasars and active galactic nuclei seen in other galaxies, which shine with energy so fierce they outshine billions of suns? Our black hole seemed different. It slept. Most of the time it sat in near total silence, feeding only on small amounts of gas and dust that happened to wander too close. The surrounding material orbited lazily, glowing faintly in infrared light. It was like watching an ancient predator resting in the dark, its power hidden, but always there. Yet, every so often, the silence broke. In May 2019, astronomers using the Keck Observatory in Hawaii witnessed something astonishing. The region around Sagittarius, a star, suddenly flared. Its brightness increased 75 times in a single night. For 2 hours, it burned like a cosmic heartbeat. Then, as quickly as it had risen, it faded back into stillness. No one knows exactly what caused it. Some scientists think a clump of gas had drifted too close and was torn apart. its atoms screaming in heat as they spiraled toward the event horizon. Others believe it was a magnetic reconnection event, a sudden release of energy from tangled magnetic fields in the accretion flow. Whatever the cause, it proved one thing: Sagittarius, a star, is not dead. It is merely resting, waiting, breathing. The black hole's feeding habits are unpredictable. Sometimes it consumes a wisp of gas or a small asteroid, and a faint flicker of light appears. Other times, whole streams of material fall in, creating violent outbursts of radiation before being swallowed forever. These flares tell astronomers about the black hole's personality. Each one reveals how matter behaves under the most extreme conditions known to physics. By studying their timing and energy, scientists can map the shape of magnetic fields, the temperature of orbiting plasma, and the turbulence near the event horizon. It's like listening to the heartbeat of a creature hidden inside darkness. But this flicker of life is not just happening now, it has been happening for centuries. In 2013, astronomers studying X-ray echoes from clouds of gas near the galactic center found something remarkable. The light reflecting off those clouds did not match the current faint activity of Sagittarius, a star. Instead, it revealed a memory, a record of a massive outburst that must have happened hundreds of years ago. It seems that around the year 1800, Sagittarius, a star, was 1,000 times brighter than it is today. For a brief time, it may have been as active as the nuclei of faraway galaxies. The echo of that ancient flare is still traveling through space, bouncing off gas clouds like a whisper from the past. It tells us that our galaxy's heart is not just a quiet anchor, it is a sleeping volcano. Most days, it slumbers peacefully, but when it awakens, it can release energy powerful enough to change the structure of the galaxy itself. Some of that energy may even reach us. High-energy cosmic rays, mysterious particles that strike Earth's atmosphere every second, could be the distant fingerprints of past outbursts from the Milky Way's center. In this way, the black hole connects everything, from the smallest atoms in our air to the largest structures in space. Even when silent, its influence is everywhere. The stars near it dance to its pull. The gas clouds bend to its will. The galaxy's spiral arms, stretching for hundreds of thousands of light-years, all move in harmony with this hidden force at their core. When we imagine our galaxy from afar, we often think of it as peaceful, a glowing whirlpool of stars turning gracefully in space. But that grace hides violence. Every spiral, every glimmer, every trace of light depends on the gravity of that single dark point. It is easy to forget that the heart of beauty can be built on destruction. The Milky Way's calm is an illusion. Its stability comes from chaos. At the center, Sagittarius, a star, holds the balance. It consumes, it releases, it shapes, and it sustains. Its hunger sculpts the galaxy's rhythm, the slow breathing of light and shadow that defines the very structure of our cosmic home. And though we see it as a black hole, it may be more accurate to call it what it truly is: the engine of our existence. The same gravity that devours also creates. The same pull that ends one form of matter gives birth to another. The death of a star becomes the light of a galaxy. Every planet, every sun, every atom around us owes its order to that silent power at the core. It does not roar. It does not glow. It simply is. And through it, so are we. But as scientists studied its behavior, they noticed something else, something subtle, something mysterious. The stars closest to Sagittarius, a star, were not only moving fast, they were moving strangely. Their orbits were not perfect ellipses. They shifted, curved, and twisted slightly over time, as if space itself were warping beneath them. This distortion was not random. It was the whisper of another secret, the proof that Einstein's theory of general relativity was not just right, but complete. And that discovery would lead us to one of the most beautiful experiments in all of science. Einstein once said that imagination is more important than knowledge. Yet his own imagination, written in the quiet of 1915, continues to describe the universe with a precision that still astonishes us today. More than a century after he proposed his theory of general relativity, the stars around Sagittarius, a star, would become the ultimate test of his vision, a test no laboratory on Earth could ever perform. To understand what Einstein predicted, we must first remember what Newton believed. Newton described gravity as a force, a pull between two masses. It was simple, elegant, and it worked beautifully for centuries. But it was also incomplete. Einstein saw gravity differently. To him it was not a force, but a shape, the bending of space and time caused by mass and energy. A planet, or a star, does not move because it is pulled. It moves because the space it travels through is curved, and it simply follows the path of that curve. Imagine stretching a rubber sheet tight, then placing a heavy ball in the center. The sheet sinks inward, curving around the ball. If you roll smaller marbles across the sheet, they spiral inward, not because the ball pulls them, but because the surface guides them. Now imagine that same effect, not on a rubber sheet, but on the very fabric of space and time. That is the universe we live in. For most of human history, this was a beautiful idea on paper, a set of equations, tested mainly through light bending around the sun, or the ticking of precise atomic clocks. But Sagittarius, a star, offered something far grander, a chance to see Einstein's theory unfold on a galactic scale. The stars closest to the black hole, especially S2, became natural laboratories of gravity. Each orbit, lasting 16 years, carried that star through regions where spacetime was warped to extremes. By tracking its motion with sub-millimeter precision, astronomers could watch Einstein's equations come alive. In 2018, the Gravity Collaboration, a network of telescopes working together as one, observed something extraordinary. As S2 completed its close approach, its light stretched and shifted just as Einstein had predicted. The effect was small but unmistakable. The wavelengths of its light lengthened due to gravitational redshift, a sign that time near the black hole was running slower. It was the first direct confirmation of general relativity in the environment of a supermassive black hole. But that was only half of the revelation. Einstein's theory also predicted that orbits near massive objects should not repeat perfectly. Instead, they should precess, slowly rotate in space with each cycle, tracing a delicate rosette pattern rather than a closed ellipse. In Newton's world, orbits were clean loops. In Einstein's world, they were spirals of time. Astronomers had seen this before in our own solar system. The orbit of Mercury precesses slightly due to the Sun's gravity, a small deviation Einstein famously explained. But near Sagittarius, a star, the effect would be millions of times stronger. For years, scientists measured S2's path with extraordinary care. When it completed another orbit, the results were clear. Its ellipse had rotated by about 12 arc-minutes, roughly 1/5 the width of the full moon in our sky. The prediction matched Einstein's equations exactly. This small twist, invisible to the naked eye, carried enormous meaning. It was the universe's way of confirming that space and time are not rigid. They are flexible, fluid, alive. To visualize it, imagine a dancer spinning around an unseen partner. With every turn, the floor beneath her shifts just a little, changing the pattern of her dance. The partner never moves, yet his presence alters the rhythm of everything around him. That partner, in our galaxy's story, is Sagittarius, a star. Its gravity shapes not only space, but also time itself. Each orbit around it becomes a kind of clock, marking how reality bends and flexes in its presence. And what makes this discovery so beautiful is that it unites two extremes, the most human and the most cosmic. The same equations that describe a clock ticking in a laboratory on Earth also describe a star racing around a black hole 26,000 light-years away. It is a single language, spoken by the universe from the smallest scale to the largest. But Einstein's success carries with it a whisper of mystery. His equations explain how gravity behaves, but not what it truly is. They show the shape of space-time, but not the substance of it. And as astronomers looked deeper into Sagittarius, a star, they realized something even stranger. Einstein's theory, magnificent as it is, begins to falter at the edge of the black hole's heart. Inside, where the equations break and infinities arise, another truth must exist, one we have yet to uncover. That realization drew scientists closer to the horizon, into a place where even Einstein's ideas begin to stretch, a place where matter, energy, and time lose their familiar meaning, a place where we confront the very edge of understanding. And so, from proof of relativity came the next question, the one no equation could yet answer. What lies beyond the event horizon? There is a point in the universe where words begin to lose their meaning, where light no longer travels straight, where time itself seems to hesitate. This is the event horizon, the edge of a black hole, the border between the known and the unknowable. For decades, it was just a line in theory, an elegant solution inside Einstein's equations. But around Sagittarius, a star, that line becomes real, a physical boundary drawn in the invisible fabric of space. Beyond it, nothing escapes. Not matter, not light, not even the idea of time. When you stand far away from a black hole, the universe feels familiar. Stars rise and set, clocks tick, cause follows effect. But as you move closer to the horizon, everything changes. The familiar begins to bend. If you could somehow fall toward Sagittarius, a star, your journey would be unlike anything you can imagine. To an observer watching from far away, you would seem to slow down. Every signal you send would arrive later and weaker. Your image would stretch, dim, and freeze at the very edge of the horizon. You would never seem to cross it. Yet from your own point of view, the story is different. You would fall freely, feeling nothing unusual at first. The stars above would warp into strange arcs of light. Behind you, the universe would appear to speed up, galaxies racing through eons in moments. You would pass the event horizon quietly, without sound, without warning. That contradiction is not illusion. It is truth. It is the dual reality that defines black holes. Two observers, two experiences, both correct. The event horizon is not a solid wall. It is a boundary of perspective. On one side, the universe continues as before. On the other, all paths lead inward. It is a place where direction itself changes meaning, where forward in time and deeper into gravity become the same thing. For an object falling in, space and time twist together. Distances shrink. Moments stretch. The very geometry of the universe rearranges itself. Every second closer means a step deeper into a realm where even light, the fastest thing that exists, cannot keep up. At the horizon, escape velocity equals the speed of light. That simple statement carries the weight of eternity. It means that once you cross, every path through space leads inward, and every future leads to the same destination, the singularity. The singularity is where the known laws of physics collapse. In the simplest terms, it is a point of infinite density, matter crushed into zero volume, gravity without limit. Space and time fold together into something that defies reason. But many physicists believe that infinity is not real. It is a sign that our understanding is incomplete. The equations break down not because nature fails, but because our theories do. Something else must exist there. Something beyond relativity, beyond quantum mechanics, beyond everything we know. Some imagine that inside, matter does not vanish but transforms, its information encoded in the fabric of space-time itself. Others suggest that the core is not a true point, but a bridge, a tunnel to another region of space, another time, another universe. These ideas are not fantasy. They are mathematics searching for meaning. They are the universe inviting us to look deeper. But there is one thing everyone agrees on. Once something crosses the event horizon, it can never return. The black hole's surface is a one-way mirror, a border drawn not by walls, but by the laws of physics. And yet even as it swallows, it speaks. The matter that spirals inward emits radiation, its last cry before falling silent. This light does not come from the black hole itself, but from the dance of particles just outside the horizon. In that dance lies the story of energy, gravity, and perhaps of information itself. The region just beyond the event horizon, where these final photons swirl, is one of the most violent environments in the cosmos. Magnetic fields twist like ropes of fire. Jets of plasma may shoot out from the poles, reaching for light years into space. These outflows remind us that even the act of destruction can create beauty. Black holes, paradoxically, are engines of creation. They drive the evolution of galaxies, shaping the birth of new stars and the flow of cosmic matter. Sagittarius, a star, though quiet now, likely did the same in its youth. Its eruptions sending shockwaves through the Milky Way, stirring gas clouds into motion, setting the stage for future generations of stars. Every world, every planet, every atom that forms us might trace its origin to that ancient turbulence. To understand the black hole, then, is not to look at death, but at transformation. It is to see how endings and beginnings are written in the same line of physics. The event horizon is the threshold where that truth takes shape. It is not just a frontier in space. It is a mirror of everything we do not yet understand about existence. And yet, as we draw closer to that line, a deeper puzzle emerges, one that challenges the very foundations of knowledge itself. Because if nothing escapes a black hole, then what happens to information? What happens to the memory of what was once real? Every atom in the universe carries information. The way its particles move, the energy they hold, the position they occupy, all of it encodes a record of what they are and where they've been. In the world we know, nothing is ever truly lost. Matter changes form, energy transforms, but the information, the blueprint of existence, remains. At least, that is what physics has always told us. But when we step near a black hole, this rule begins to tremble. If a black hole swallows everything, light, matter, energy, even time, then where does the information go? Does it vanish? Or does the universe keep a secret archive, hidden beyond our reach? This is the question that has haunted physics for half a century. The black hole information paradox. It began with Stephen Hawking in the 1970s. Using the laws of quantum mechanics, he showed that black holes are not completely black. They emit faint radiation, now called Hawking radiation, caused by tiny fluctuations in the vacuum of space itself. According to his calculations, this radiation carries away energy, slowly draining the black hole's mass over unimaginable stretches of time. Given enough trillions of years, even the largest black hole would eventually evaporate into nothing. That idea was shocking enough, but it carried a deeper implication. If a black hole can vanish, then everything it swallowed vanishes with it. All the information about every star, planet, or particle it consumed would be erased from the universe forever. And that, in the language of physics, is forbidden. Quantum mechanics insists that information cannot be destroyed. It can be scrambled, hidden, or transformed, but never lost. The universe must always keep a perfect record of itself. If Hawking was right, then quantum theory was wrong. If quantum theory was right, then our understanding of black holes, and perhaps gravity itself, was incomplete. For decades, the debate divided physics. It became a riddle that stretched across generations. Some sided with Hawking, believing that information was truly lost inside the singularity. Others believed it must somehow escape, encoded in the radiation itself, or imprinted on the surface of the event horizon. To make sense of it, scientists began to imagine the black hole not as a void, but as a kind of cosmic hard drive, a place where information is stored in the faintest ripples of space-time. This idea led to one of the most extraordinary concepts in modern physics, the holographic principle. It suggests that everything inside a region of space can be described by information written on its surface. In other words, what happens inside the black hole might be fully encoded on the event horizon, like a three-dimensional world projected from a two-dimensional film. In this view, the universe itself could be holographic. Every particle, every force, every moment might be a shadow, cast by a deeper layer of information woven into the structure of space-time. It sounds abstract, even poetic, but it may be the key to uniting Einstein's relativity with quantum mechanics, the dream of a single, complete theory of everything. Some physicists think the answer lies in the subtle patterns of Hawking radiation. Perhaps the radiation is not random after all. Perhaps it carries in microscopic detail the information of everything that ever fell into the black hole. To us, it would appear as noise, but beneath the chaos could lie the universe's most meticulous archive. Others believe that black holes act like mirrors. When something crosses the horizon, its information is reflected back, smeared across the surface, preserved but inaccessible. Then there are those who propose something even stranger, the idea of firewalls. A firewall, in theory, would be a zone of unimaginable energy at the event horizon, where incoming matter is incinerated instantly. This would destroy information, but only from the point of view of the falling observer. For the universe outside, the information might still be safe, recorded in the radiation escaping outward. These ideas are not settled science. They are pieces of an unfinished puzzle. Each theory offers a glimpse of truth, but none yet fit together perfectly. What makes the paradox so haunting is that it is not just about physics. It is about meaning. It is about whether the universe keeps its own history, or whether some moments once lived are gone forever. If information can vanish, then the past can truly die. If it cannot, then every second of existence, every star that burned, every life that lived is written somewhere, indelible and eternal. Perhaps the event horizon is not a wall of destruction, but a boundary of transformation. Perhaps when matter crosses it, the information it carries is not erased but rewritten, woven into the deeper structure of reality. It is a comforting thought, in a cosmic way, the idea that nothing is ever truly lost, that the universe, vast and cold as it may seem, remembers everything. And yet, there is a deeper mystery still. Because beyond the horizon, beyond the layers of light and information, lies the singularity, a place where even memory itself seems to end. It is there, at the very heart of Sagittarius, a star, that the universe stops making sense. What happens there is the final question, and perhaps the one we may never be able to answer. There is a point inside every black hole where all of our equations, all of our understanding simply fall apart. Physicists call it the singularity, but that word doesn't really explain it. It hides our confusion behind a simple label. At the singularity, matter is crushed into a state that defies imagination. Density becomes infinite. The curvature of space-time turns inward beyond measure. Every known law of physics stops working, as if reality itself has reached its breaking point. For most of the universe, Einstein's theory of general relativity is flawless. It predicts how planets move, how stars live and die, how galaxies evolve. But at the singularity, relativity collapses under its own weight. It describes a place where gravity becomes infinite and time no longer flows. That cannot be the full truth. Infinity, in science, is a red flag. It means we've reached the edge of our understanding. Imagine compressing the Earth down to the size of a marble, then compress it again, and again, until even atoms collapse, until protons and neutrons merge into one continuous blur of energy. Keep going. In theory, a black hole keeps collapsing forever, but nature rarely works with forever. Something must happen before that final step. Some scientists believe the singularity is not a point at all, but a region, a dense core where quantum effects, the smallest laws of the universe, take control from Einstein's smooth geometry. Quantum mechanics tells us that nothing can be precisely fixed. Position and momentum, energy and time, all are uncertain. That uncertainty might prevent total collapse. Instead of a true singularity, the black hole's center could be a chaotic sea of fluctuating energy, a storm where space and time lose all shape. Others propose that the singularity is a doorway. In certain mathematical models, when space-time bends to infinity, it doesn't end. it tunnels through to another region of the universe, perhaps even another universe altogether. If that were true, every black hole could be a bridge. Matter falling into Sagittarius. A star might reappear somewhere else, far beyond the Milky Way, or in an entirely new cosmos. We don't know if these possibilities are real. We may never know. No signal, no particle, no piece of information can return from beyond the event horizon to confirm it. The singularity remains a perfect secret, guarded by the most fundamental law of nature. Once inside, nothing escapes. Still, physicists refuse to give up. They are searching for a theory that can unite Einstein's relativity with quantum mechanics, a theory of quantum gravity. String theory offers one possible path. It replaces the idea of point-like particles with tiny vibrating strings, each string a note in the cosmic symphony. In such a universe, there are no true points, no infinite densities, only loops of energy so small and tense that they define the smallest scale of reality. If this idea is right, singularities might not exist at all. The collapse would stop at a finite limit where quantum vibrations push back against gravity's pull. Another approach, loop quantum gravity, imagines that space itself is made of discrete chunks, like pixels on a cosmic screen. These tiny atoms of space can bend and twist, but not infinitely. That too could prevent singularities. Instead of an infinite point, there could be a bounce, a moment when collapse reverses, possibly giving birth to a new universe on the other side. Every theory, in its own way, suggests that the singularity is not the end. It's a transition, a transformation, a place where reality sheds one form and takes another. But for us, watching from light years away, it remains an unreachable mystery. If you could fall into Sagittarius, a star, your journey would be one way. At first, you'd see the stars behind you fade. The pull of gravity would stretch you, gently at first, then more fiercely, until your body elongated like a strand of light itself. Time would slow, space would narrow, and then everything, your body, your atoms, your very sense of self, would blend into the flow of the universe. It's horrifying and beautiful at once. The thought that the same gravity that holds our feet to the ground can, somewhere else, erase the concept of ground entirely. The singularity is not just a physical boundary. It's a philosophical one. It is the edge of human thought. Beyond it, even our definitions of existence and time no longer apply. Perhaps, in the most profound sense, that is its lesson. That there are still places in the universe where mystery reigns, where equations give way to awe, where science, for all its brilliance, must whisper, "We don't yet know." And yet, even this deepest void is not forever. Even the most powerful black hole, even Sagittarius, a star, cannot escape time's final judgment. In the farthest future, when every star has faded, when every atom has cooled, when the universe itself grows cold and silent, something astonishing will happen. The black holes will begin to die. In the beginning, black holes seemed eternal. They were the final word in destruction, the ultimate one-way door of the cosmos. Once matter fell in, it stayed there forever. Once formed, they were thought to live without end. But the universe, it seems, allows no immortality. Even the darkest giants must one day fade. In the 1970s, Stephen Hawking discovered a quiet truth hidden in the mathematics of quantum theory. It began with a question so simple it sounded absurd. What happens at the very edge of a black hole? Space, according to quantum physics, is never truly empty. It constantly flickers with pairs of virtual particles, one positive, one negative, popping into existence, then annihilating each other in fractions of a second. Normally, this leaves no trace, but near the event horizon of a black hole, the balance breaks. Sometimes one of these particles falls inward while the other escapes. The one that escapes becomes real, a faint whisper of radiation traveling into space. The one that falls in has negative energy relative to the outside universe, slightly reducing the black hole's mass. This delicate exchange is called Hawking radiation. It means that black holes are not truly black. They glow, dimly, invisibly, but inevitably. The process is unimaginably slow. For a supermassive black hole like Sagittarius, a star, the loss is so tiny it's almost poetic. It emits less energy than a single atom of hydrogen releases in 1,000,000,000,000 years. Yet, over unthinkable stretches of time, the effect accumulates. Every escaping photon, every quantum ripple, carries away a fragment of the black hole's mass and memory. Slowly, silently, it shrinks. At first, nothing noticeable changes. Billions of years pass, galaxies drift apart, and still the black hole holds its power. But the universe continues to expand and cool. The stars fade. The cosmic background radiation, the faint afterglow of the Big Bang, grows colder and weaker. One day, far beyond the span of any civilization, the universe will be dark. No new stars will form. The last red dwarfs will flicker out. The cosmos will belong to the black holes. For trillions upon trillions of years, they will dominate the night. Invisible engines of gravity, each one a remnant of a vanished era. Then, the balance will shift. When the surrounding universe cools below the black hole's temperature, the slow trickle of Hawking radiation will no longer be absorbed, but will begin to escape faster than it can be replaced. The giant will start to evaporate. For Sagittarius, a star, that moment lies in a future so distant that human language can hardly describe it. Roughly 10 to the power of 97 years. That's a 1 followed by 97 zeros. To grasp that timescale is impossible. If the entire age of the universe so far were reduced to a single second, the black hole's lifetime would still stretch beyond comprehension. But in the end, even eternity runs out. As it shrinks, the black hole grows hotter. Its radiation strengthens. What was once a whisper becomes a roar. The temperature climbs to billions of degrees. The final moments arrive in a storm of energy and light. When a black hole has consumed everything and has almost nothing left, it releases it all. In an instant, the mass of millions of suns converts into pure radiation. A final flash that outshines entire galaxies. And then, silence. The monster that once anchored the Milky Way, that held hundreds of billions of stars in its invisible grip, will be gone. Its energy scattered across an empty universe. What remains after the last black hole dies? Only the faintest particles, drifting endlessly through expanding space. No light, no warmth, no structure. Just the quiet persistence of existence itself. Yet even that emptiness carries a strange beauty. Because from beginning to end, the universe follows one perfect rhythm: creation, transformation, and return. The black hole's birth came from collapse, from a star that fell inward under its own weight. Its life was a long reign of gravity, shaping galaxies and stars. Its death, through Hawking radiation, gives that stolen energy back to the cosmos. Nothing, it seems, is wasted, not even the darkness. When Sagittarius, a star, finally vanishes, it will close the last chapter of the Milky Way story. The spiral arms that once glimmered across the sky will be long forgotten. The planets, the stars, even the memory of life will have dissolved into dust and light. But in that final flash, every atom that ever fell into the black hole, every particle from every star, every photon from every sun, will return to the universe, set free again. And somewhere in that last burst of energy, perhaps the information that once fell beyond the horizon will emerge too, rearranged, scattered but never truly lost, because the universe, for all its darkness, seems to remember everything. Even its endings carry traces of its beginnings. In that sense, the death of a black hole is not destruction. It's balance. It's the quiet restoration of the cosmic ledger. From gravity's first pull to its final sigh, everything that ever was, every motion, every star, every breath, is part of one continuous story. A story that began in light, was shaped by darkness, and ends perhaps in both.